So we have a relationship to relate the pressure drop to the friction factor, but now we need to find some friction factors. So we're going to start by just looking at the friction factor for laminar flow. And we have a solution for laminar flow that relates the pressure drop. Remember, this was the pressure gradient to things like the average velocity, the viscosity, and the pipe diameter. So again, this is for circular pipe flow. So we're looking at circular pipe flow, and we're looking at the pressure gradient here. If we want a pressure drop, that's very easy. P in minus P out is equal to minus G over minus GL. So the pressure gradient, P in minus P out, it's whatever the pressure gradient is times the length of the pipe. So that's pretty simple. So now we're going to go ahead and put that pressure drop on the left-hand side here. So we have GL, so we have delta P is minus GL. So delta P, I got to put this in here. So delta P is equal to just U8 mu over R naught squared. That's my negative G, and then L. So I have L there. And now I can set that equal to the friction factor formula for pressure drop. So we know from the pressure drop in terms of friction factor is L over D U average squared over 2 times rho. That's what we learned last lecture. So we can set these two things equal to each other. So we set this one equal to this one. So this is the laminar flow solution, and this is the relationship for friction. Pressure drop is a function of friction factor. So we're going to say that U8 mu over R naught squared times L is equal to FL over D times U squared over 2 rho. And now we can solve for F. So that's what we're going to do. We can cancel a couple things. The L cancels right off the bat. This U cancels one of those U's there. So we lose a few things, but we have plenty of things left. Put F on the left side now. This 2 is going to come across and give me a 16 in the numerator. I've got a mu in the numerator. That's it for numerator stuff for me. Then I've got U is going to come into the denominator, and it looks like rho is going to come into the denominator, and I still have R naught squared in the denominator. So that looks like, oh, I lost D. There, D is in the numerator. All right, so there's my friction factor in terms of all this stuff. So I have a friction factor in terms of average velocity, but I can do better than that. So first I'm going to recognize that I have D and R here. So that's silly because I can use either D or R. I'm going to switch to D. So I have 16 mu, and then I have D here, but I'm going to use U rho D over 2 squared. So that's going to be equal to 16 mu. That D is going to cancel. So I'm going to have U rho D over 4. And I can put that 4 up in top. So I'm going to move that, multiply up and down by 4. And that's going to give me 64. So I have F is equal to 64 mu over D average U rho. Well, that's kind of odd, but that's what it is. And let's try to clean it up even more. So I have mu and rho. And when I have mu and rho, I start thinking about nu, right? So I'm going to multiply up and down by, let's see, 1 over rho. So 64 mu over rho, and then D average U rho over rho. So of course rho over rho is just going to be 1. So F is equal to 64 mu over rho is nu. And then I have U average D down in the bottom. This grouping, hopefully you recognize it now, that's a Reynolds number. So the Reynolds number based on D is U D over nu. So my friction factor has the very simple form 64 over the Reynolds number based on D. So that is the friction factor for laminar pipe flow. It's a little unclear why you'd ever want this. I mean, we know how to solve for laminar pipe flow directly. We don't really need to resort to using the friction factor, which is kind of an odd tool for this particular problem. But it does allow you to compare friction factors for laminar flow versus the friction factors we'll see for turbulent flow, in the next lecture. So simple result, but perhaps not the most useful.